Now let's take a look at the LT3080 datasheet, because we might find some practical considerations in here. In fact, I guarantee we'll find some practical considerations in here that we have to take care of if we want to actually build this thing, as opposed to just doing a conceptual type top level design schematic that we've been doing up until now. And I really like this device because it does just exactly what we want. Now let's have a look at some of the specs. Output current up to 1.1 amps. So I'm going to use the TO220 package of this. It's available in many different packages, a DFN, a DPAC, and a SOT223 version, which is really nice, or an MSOP package, but we'll use the TO220. It's really neat. 1% initial accuracy on the set current. That's not bad at all. And one of the neat things about this is that a single resistor programs the output voltage, although we're not going to use that today, but we might have to take aspects of that into account, as you'll see. But it's really neat, unlike the LM317, where you've got to use two resistors to actually set the output voltage. This one only needs one, and we'll go into why. Low output voltage noise, it's only 40 microvolts RMS through in that bandwidth, and it supports input voltages up to 36 volts. Terrific. We're not going to go that high today, but hey, if you're into high voltage power supplies, it can do it. And the dropout voltage, that will be at full load, is only 350 millivolts, but we can check the curves on that one, as you'll have to. Less than 1 millivolt load regulation. Line regulation's awesome. Now, one thing, minimum load current, there it is, 0.5 milliamps. We have to worry about that. And it's stable with 2.2 mic ceramic output capacitors. That's all you need to make this thing stable, and then it's guaranteed over any load you like. Terrific. And of course it's got fallback current limiting and over temperature, so it's pretty bulletproof, just like the LM317. And there's the typical application, which we've just spent a long time talking about. You've got the series pass transistor, the error amp connected straight through, but instead of having an internal voltage reference like the LM317, it's got an internal constant current generator, which is actually 10 microamps, and it tells you that over here. Here's the distribution graph, and you'll notice, we've been talking about bell curves recently. Well, there it is again, and that is 10 microamps constant current down through there. Now, although it doesn't tell you this in the data sheet, it basically implies that because this is only 10 microamps, this constant current generator, it's pretty darn wimpy, right? You can force a voltage into the set pin just like you can on the LM317, and it's going to be no big deal at all. But got to remember, there's an extra 10 microamps which has to flow out through there, and we'll see that matters later. And we'll just have a quick browse through the characteristic spec table here and see if there's anything that takes our fancy, shall we? Now, set pin current, as we've said, is 10 microamps. We don't necessarily need to know about the min-max values of that because we're driving it. We're not using an external resistance. We're just driving that pin hard. So really all we care about is that typical figure, which we'll use later in a simple calculation. Now let's take a look at the output offset voltage, and what this is V out minus V set. What that means is the actual output voltage, the real output voltage, minus what you've actually set, what you've set on your adjustment pod, or what your software has set, and what you're driving into that V set pin in this case. Now these specs are for a control voltage of a V in of 1 volt with an output current of 1 milliamp. Now it could be your actual value may be plus minus 2 millivolts. Look at that. So it may not be spot on to it. If you put exactly 1 volt on that V set pin, if you're driving that V set at 1 volt, then it could be 2 millivolts either side of that. Not a problem in the case of this power supply. 2 millivolts, that's neither here nor there. But if you're designing precision, really precision applications or precision power supplies, then this sort of thing can matter, and you've got to take it into account. Now, and you'll notice this dot next to it, it's actually wider than that over the full temperature range. It tells you up here. Bingo, little trap. The other spec there is only for an ambient temperature of 25 degrees Celsius. And remember, this is not the ambient temperature, it's going to be the junction temperature of the device itself. So it's dissipating all that power and your heat sink's gone up to 60 degrees. Well, your lab might be 25 degrees, but your heatsink and your device is at 60 degrees, so just beware. And you'll notice that there's two different specs here, depending on the different packages. And the reason that they have these is because the die used, the silicon die, is going to be different in these smaller packages as they have a larger die used in these larger power type packages, and the spec gets worse. Plus minus 5 millivolts. Oh, man, terrible. Or plus minus 6 millivolts over temperature. Who cares for our case, but you know, you've got to be aware of that sort of stuff. The thing the output offset voltage is fairly critical for is when you parallel devices up. And this is how you're going to increase the output current, because this device is only rated to just over an amp. What if you want 2 amps or 3 amps or something like that? Well, you can parallel devices up like this, and all you've got to do is include a series ballast resistor like this, and you can do these do this to any similar type of voltage regulator as well. Now, there is an alternative device, the LT3080-1. I think it's a bit rarer to get, but it actually includes a built-in ballast resistor in there. And the output offset voltage, a small one like the plus minus 2 millivolts you see here quoted for this one, or at least nominal at room temp, if it's tight like plus minus 2 millivolts, it means that your output ballast resistor only has to be very small. In this case, they recommend 10 milliohms output resistors, and it's still going to share 80 to 90% of the current between two devices, or even better than that typically. And so you don't even have to actually buy a resistor for that. It's good enough to actually use a PCB trace for that. And they actually tell you they actually recommend that a 10 mil width or a 10 thou width trace on a PCB, 20 thou width trace, typical 1 ounce or 2 ounce copper. 1 ounce is your normal weight copper, or if you're designing heavy duty power supplies, you might have ordered a 2 ounce copper PCB. But you can get your ballast resistors. You don't actually have to buy one. There's no extra bill of materials item and cost. You just include it with a PCB trace. Brilliant. And as long as that value is high enough, then you can share the current between the two devices adequately without one device heating up much more than the other device. But you can't make it too high, because then you get a voltage drop. And in this case, let's say you got a 2 amp output and our two ballast resistors are 10 milliohms. Well, it's a total of 5 milliohms because they're actually in parallel. It's essentially what they are. So that's 5 milliohms ballast resistance or output resistance there at 2 amps is going to give us a 10 millivolt drop on the output. And that's not too bad. At 1 volt, that's only 1%. So the neat thing about parallel devices like this is that you can actually leave one of the footprints unpopulated, or multiple footprints on your board. If you're designing a power supply like this and you want to save a bit of cost to begin with, or you're designing a kit or something, save a bit of cost, you only have one device. Or if you want 2 or 3 or 4 or more, you can actually parallel them up and you can just solder in the individual devices as you need them. Load regulation is going to be excellent from 1 milliamp up to, it's fully specified from 1 milliamp up to 1 amp, no problems. Line regulation up to 25 volts input, not a problem. It's specified at 1 milliamp load. Oh, no, don't need to worry about that. Minimum load current. Now, here we go. Minimum load current, very, very important. We need to take that maximum figure there, 500 microamps or half a milliamp, as our minimum load current. If we don't do that, it doesn't tell you what's going to happen. There's a couple of notes here which we'll read, but it doesn't tell you. Just assume that's not going to be stable, or it's going to have a larger dropout voltage, or it's not going to allow you to go down to as low a voltage as it could, or whatever. There's a whole bunch of different reasons not to. If you don't meet that, a whole bunch of bad things can happen and ruin your day. So we have to somehow get a minimum load current over our minimum load current of 0.5 milliamp over our entire voltage range, and it's only specified at a VIN range of 10 volts. If you go higher, it needs 1 milliamp minimum. And there it is, note 3, minimum load current, yada yada, quiescent current. And it's the minimum load current required to maintain regulation. If you don't meet it, it ain't going to regulate. And that defeats the whole purpose of a power supply. Now, the dropout voltage of this part is interesting because it specifies it in two different ways. There's V control pin dropout voltage and V in dropout voltage. So if you look back to the circuit here, it's got V in and V control. Normally you tie these two together, and we will in our application here today, but if you want a really low dropout voltage of this part, like a low input voltage and a minimum input dropout voltage between the input and the output, but you happen to have in your circuit somewhere a higher control voltage, then you can take advantage of that and get a lower dropout voltage from in to out by tying V control up to a higher voltage up there like that. But we're going to tie them together, and also not all parts have the extra V control pin. Some of the packages actually will tie those two pins internally, so you don't have it available. So we need to take the worst case version of that, because we're tying them together, which will be, there it is, 1.2 volts, or at full, that's at 100 milliamps, or at full current, which you have to take into account, it could be as bad as 1.6. So our input voltage has to be at least 1.6 volts above our output voltage. And that's this voltage here, not over here. So if our output voltage is 5 volts here, we need to have at least 6.6 volts or 1.6 volts higher here. And if we are using a 1 ohm resistor and we're drawing an amp, you're going to get an extra volt. And so you need 7.6 volts here, minimum, for a 5 volt output. And the current limit here on maximum output voltage, typical 1.4 amps, but you might be able to push it that far, and you probably can, but when you're designing and you want to set your maximum figure, the lowest one here is what you're going to use, as opposed to, say, the minimum low current, you'd use the highest value. In this case, you want to be conservative and use the lowest. So depending on the parameter, you either have to choose the maximum value or the minimum value. We'll choose 1.1 amps. That's what our circuit will be capable of. Now, as far as the output noise goes, most linear regulators are pretty darn good, and this one's no exception. 40 microvolts RMS for the error amplifier noise. Now, if we have a look at the error amplifier here, all of the noise, assuming that the input voltage is perfect and there's no noise coming in there, then all of the noise is going to be generated by the internal current source and the error amplifier. So that's basically all the noise internally is going to be that 40 microvolts RMS. So even if we force in an absolutely perfect voltage onto here with no noise at all, we're still going to get 40 microvolts or thereabouts, worst case RMS output noise. But as you can see, the set, because this is a direct feedback loop and whatever voltage you put on here comes out here, any noise that you put on this set pin is going to come out here as well, within limits of bandwidth and all sorts of other things like that. So really the noise limit will depend on this. Now, if you're driving your circuit with a pot like this and you've got this fed to a voltage reference or something like that, say a 2.5 volt voltage reference, a really quiet low noise voltage reference, then your noise is going, and you're driving that pin directly, then the noise is going to be pretty good. But if you're doing a PWM signal and you're feeding that through your RC filter like that, and then you're driving that with a buffer, obviously, and you're driving that into the set pin like that, then your noise, then any noise that you haven't filtered out here, any noise on there, is going to make it through to here, and it's going to make it through to your output. So filtering, if you're using microcontroller control, filtering of your pulse width modulated signal is important. But you can really up these values. You can, up them as high as you want to really, absolutely slaughter any noise and just kill it dead. It's not that hard. You just need to choose high values. And if you want to care about the ripple rejection, then you have to figure out what 75 dB is for your various input ripple, which is specified at 0.5 volt peak to peak. If you're powering this thing from a transformer and a bridge rectifier and a filter cap, you're going to get 100. This is a full wave one because it's double 60 hertz, so it's 120 hertz ripple there. It's specified. That's pretty good, and you can calculate that if you're using a noisy input and you've got ripple. But if you're using, say, a battery input or something like that, then you don't have to worry about that at all. But if you actually want some real figures, you can plug those in for 75 dB there at the nominal 0.5 volt peak to peak, and that's going to give you an output noise of less than 100 microvolts. So 100 microvolts doesn't sound like much, and it's not. It's it's down in the noise. Although once again, if you've got a really low noise, very high spec power supply system, then it could matter. But just for a lab power supply like us, more than good enough. Order of magnitude good enough. But that's only at 120 hertz. That's for ripple, AC mains ripple, if you're powering this thing from an AC mains input. What if you got a switch-in frequency of 10 kilohertz or 1 megahertz? Well, where would you get that from? Well, if you're powering this regulator, if this regulator is being, the LT38 is being powered from a DC to DC converter, well, that's going to have a switch-in frequency, and that's going to have output noise, and a very high efficiency switch-in regulator might be up near a megahertz or something like that. And in that case, look at the rejection there at 1 megahertz is down to only 20 dB. That's a huge drop from 75 dB at 120 hertz. And if we calculate what 20 dB is, just like 75 dB there is, you know the formula, you've seen it before, dB equals 20 log. In this case, it's going to be V out, or our noise or ripple output voltage, over our V in this case, which is given as 0.5 volts. And if you calculate that, and if you change the formula around, because dB is already known, and you work out what your output ripple or output noise is going to be, then it's going to be 1/10 of your input noise. So if your input is 0.5 volts, you're going to get 50 millivolts output noise. So it's not down in the microvolts region anymore, it's in the tens of millivolts. And that can ruin your day if you're designing precision apps and you haven't adequately filtered your input noise like that. Now, if you were actually using this in its traditional configuration with the external resistor, and you were reliant upon the pin set current at 10 microamps, you'll see that that's only nominal at 25 degrees C. When you actually go up or even down in temperature like this, it does vary a bit. If you go right up to 100 degrees and go up an extra 50 nanovolts, woohoo! But that could be significant. And remember, when you're looking at these curves, don't fall into the trap of thinking that your product is only operating at ambient temperature at 25 degrees. It's not. This is the junction temperature of the actual device itself, the die temperature. And because this is a power supply and it's dissipating power, that junction temperature could easily get up to 100 degrees, depending on how you do your thermal design. So if you're designing really precision power supplies, you need to take that sort of thing, or any power system that dissipates power, you've got to take these thermal graphs into consideration. And the offset voltage, once again, doesn't really matter for our application, because this is versus load current. So the output offset voltage in millivolts is actually going to drop based on the output load current. So if the output load current's 1 amp here at ambient temperature, or C, it tells you here, TG, junction, the temperature of the junction, not just the ambient temperature, because ambient temperature makes no difference to it at all. All it cares about is temperature. Anyway, you're almost going to be 0.5 millivolts offset there. And if your junction's up to 125, 0.75 millivolts offset. And if you're designing precision applications, that could matter. Take it into consideration. Now, looking at the minimum load current, which is quite important, as we said, because we have to take this into consideration, then at input to output differential of 1.5 volts, then your minimum load current only needs to be 0.3 milliamps. But when it rises, your input to output differential rises to a much bigger voltage, then your minimum load current needs to be higher. So you might put in 0.5 milliamp. That's what it tells you in the top level specs, but you might say design it for 1 milliamp just to be on the safe side if you didn't care about wasting that extra 0.5 milliamp. Now, this load transient response here, we do want to consider this because this tells us our typical performance. When you change your load like this, here's the output load current in hundreds of milliamps. So we're doing a 200 milliamp jump in the load current. It goes from 50 milliamps up to 250 milliamps and then back down. And you can see what the output voltage, how it deviates, because these regulators aren't perfect, okay? They have a transient response when your output current suddenly changes. And this is the transient response you'll get if you've only got 2.2 microfarad ceramic cap. You can expect it to change by 50 millivolts output. You can expect it to droop down like that and then recover like that. And if you use a 10 microfarad ceramic, you can see that it takes a bit longer to recover, and the droop isn't, well, in this case, the rise isn't quite as much. So there you go, but that's at a nominal 1.5 volts output, but the greater your output, the greater the output capacitance on your regulator, the better your load transient response can become. But just be careful. You don't want to put a massive amount of capacitance on the output of a constant current power supply like this, because that capacitor can store a lot of energy. You know, if you put in I'm going to put in a big 2200 microfarad capacitor, that'll really, you know, give it lots of transient performance. Well, there's a downside to doing that, and that's when this thing switches into constant current mode, then it can't react because it's still got all this energy in the cap that can get dumped high current into your load because it's not current regulating. So you want to keep in a lab power supply like this with a constant current circuit like this, you want to keep the output capacitance as low as possible just to ensure stability in your regulator. Although I guess you could say, okay, you might determine transient response is a more important thing than switching over into constant current, but generally you're going to want to keep that thing, the output capacitance, low. So we're probably going to want it just, you know, the same value or twice the recommended value, just to be on the safe side, that it recommends for stability of this particular regulator. And just for a bit of completeness there, you've also got line transient response. Generally not important in a power supply design like this because our input, basically this means line transient. Line means your input voltage coming into your voltage regulator, as opposed to load transient response, which is changing current on your output. So input line transient, the power supply that's powering your power supply is generally going to be pretty stable, and it's not going to change by this sort of current like this, this sort of voltage. This is, in this case, it's got a 3 volt step in your input voltage to your voltage regulator. You can see that the output gives a droop like that of 25 millivolts. So there you go. Not important, but just thought I'd mention it. Another thing to consider is the turn-on response of the regulator, and that's what happens to the output voltage here when your input voltage ramps up. And you don't want it to overshoot by a massive amount because that can damage your circuitry if it's already hooked up to the power supply. So this one looks pretty good. It looks pretty well behaved, and we'll actually, when we build this thing up, we'll actually check that. Now here's an interesting graph. You don't normally see these. This is a bit rare. It's the residual output voltage with less than minimum load. So it's basically telling you, implying how this device is going to perform if you don't meet that minimum load current requirement. And you know that one of the big banner specs, one of the big highlight banner specs of this voltage regulator is how low the output voltage can go. It can go all the way down to 0. That's what it claims, but only with a minimum amount of output current. And that's what it's basically saying. And this is your test resistance here. So as your test resistance gets lower and the output current increases, then let's say you've got a test resistance up here of 2K. Okay, let's say 5 volts. There we go. 5 volts at 2K. And if you've got a 2K output resistor with an input voltage of 5 volts here, when it's trying to set, you see the set pin is grounded here, so it's trying to set 0 volts output, but you don't get 0 volts. You get, there you go, 0.55 volts or something like that. Terrible. So that big banner spec that it shows on the front page here, it claims, output adjustable down to 0 volts. Fantastic. Yeah, here's the devil in the detail. It only goes down to 0 volts if you've got a 0 ohm output resistor, effectively. So if you've got a 1K output resistor nominal on there, you're only going to be able to go down to about, 0.25 volts or something like that. And herein lies the trap. How do we get a minimum output load current here on an adjustable power supply? Because if we we could just stick a resistor here on our circuit down to ground, make that 1K, no worries. We're easily going to meet our minimum load requirement. Let's say it's 1 volt. Even at 1 volt, we're going to get 1 milliamp. That easily meets our minimum load requirement of 0.5 milliamp. And we can probably go down to 0.5 volts output. We're going to get 0.5 milliamps. Great. Okay, that sounds like a good solution. But what if our output voltage is 10 volts? Well, we've got 10 milliamps, and we're effectively pissing away 10 milliamps there just on that output resistor. And here's the thing to consider: if you're trying to get milliamp accuracy over here with your constant current setting, let's say you want to adjust it in 1 milliamp steps, your input voltage down here 0 to 1 volt, you want to adjust it with your micro in 1 milliamp steps. Well, geez, you've got 10 milliamps at 10 volts. In fact, you've got an output current which changes based on the output voltage. So your microcontroller over here that's driving all this thing will have to be smart and know, well, it knows what the output voltage is because it's setting it through here. So it will have to know that the load's 1K and then take that into account and then compensate by driving, instead of driving, let's say you wanted to, adjust this to 5 milliamps, and that'd be 5 millivolts. Well, if you're drawing an extra 10 milliamps out of here, you've got to actually make, because you want 5 milliamps, only 5 milliamps max to go into your load. So you know that you're going to, say at 10 volts output, you're going to have 10 volts coming out of 10 volts on here, 10 milliamps going down here. You have to actually compensate and set this one to 15 millivolts to know. And it all gets quite ugly. So if you use a fixed resistor like that, that's not a very elegant solution. I don't necessarily like it on a variable power supply like this. And by the way, another little trick, if you really care about how much current this whole thing draws, you might want to add an LED in there like that, and that could be your power LED. And so you get 2 for the price of 1. So instead of wasting your LED current just lighting up a power LED, you might get it from the output, and you can use it as an output LED or something like that. But then it doesn't work down at low voltages if this thing goes down to 0 volts or 1 volt, or it's ugly. Anyway, I reckon we need to find a better solution than the fixed resistor. So what do we use for that output current? Well, I can't think of anything better than the classic LM334 constant current source. It's a single resistor. It's available in a TO92 package. It's not bad. It goes down to very low currents, up to 10 milliamps maximum. And so I reckon we set this sucker for a value of 1 milliamp. Now, the LM334 has been around since pretty much the dawn of time. It's one of those classic devices that is still incredibly useful today. It operates from 1 volt up to 40 volts. It's got good current regulation. You can programmable current from 1 microamp to 10 milliamps. 2-terminal operation, 3% initial accuracy if you actually care about the absolute accuracy. We're not that fussy at all. It could be 10%. We couldn't care less. And it's available in a TO92 package or an SO8. So very, very usable. Cheap as chips. I love it. One thing we do care about though is its minimum operating voltage of typically 0.9 volts up to 1 milliamp. So we plan to operate it at 1 milliamp or thereabouts, or half a milliamp maybe. So unfortunately it's only going to operate down to about 0.9, maybe 0.8. But hey, 0.8 mil. If we can get our power supply to operate down to say 0.8 or 0.9 volts, that's a lot better than the 1.25 volts you might get on an LM317. And then you can go right down to 0 if you want, but then you're reliant upon the load actually providing the minimum current. Then you can't use like a high impedance load actually below 0.9 volts or 0.8 volts or thereabouts. And 0.8 volts is a nice figure, and 0.9 is nice because for a power supply to go down to, is because a single cell battery, a single cell, D cell or AA alkaline or something like that, will be basically pretty much dead from down to 0.8 volts or 0.9 volts. So a power supply that can go down that low is pretty good, and it can go lower, but depend on the load. Hey, that's good enough for me. I like it. And it's really easy to use. It's only a 3-pin device, and you have a single set resistor like this, voltage in like this, I set. This will be connected to ground down here, and this will be our output voltage, and we'll have a single resistor like this. And what value does it need to be? Well, you can go through all sorts of formulas and take into account bias currents and stuff like that, but hey, we can cheat and do the, look at this graph here, set 68 ohms, and bingo, look, it settles at 1 milliamp. So it looks like it's 68 ohms will give us 1 milliamp. 68 ohms is a nice E12 resistor value. I love it. And as you can see, it operates down to 0.8 volts, no problems. It drops off a little bit. It probably drops, it probably dies at half at 0.8 volts. That's probably as low as it's going to go, because we are operating this thing at, we want a minimum load current of half a milliamp. So really, it's going to operate down to, there it is, half a milliamp is somewhere in there, around about 0.8 on the graph. So if we set it to 1, hey, we're going to be happy. We could go up to here and then get some extra voltage margin. If our set was up there at, 5 milliamps, we can set it higher like that, and get a bit more margin for our output voltage, but I don't think we need to do that. And if your output current doesn't happen to fall on one of these characteristic curves on this graph, if you were 2 milliamps or something, you will have to use these formulas, and you'll have to take the bias current ratio into account, which changes with your output current, and that's the ratio that you can plug into various formulas down here to calculate your resistor value. Now, you remember this 10 microamps current we've talked about quite a few times from this set pin on this LT3080. It doesn't just magically disappear when you drive that pin. It's got to flow out of there. It's a constant current generator. So it's got to flow out of that pin into that resistor, and assuming that we're in constant voltage mode, all this stuff has vanished, it's got to flow out of here as well. And if we're trying to set 1 volt on our input here, sure, we'll get a volt here, but then it's going to be, there's going to be an offset error there due to that 10 microamps current. It doesn't sound like much, but Ohm's law, do the math, 10 microamps through 2K, there is 20 millivolts. Once again, doesn't sound like much, but if you're trying to set 1 volt on the output there, that's a 2% error. It's horrible. Don't want that. So what do we do about it? Now, there's 2 things we can do about it. The first one, the obvious one, of course, is to lower these values until it gets to a point where you don't care anymore, and that's a perfectly reasonable design technique. But in this case, well, we don't want to lower it too far. We could halve it down to use 470 ohms or 220 ohms or something like that. But ultimately, when you short out this op amp at high voltages, you're going to have a lot of excess current flowing out of there, and well, you're just pissing that current away. So I don't really like that solution at all. So the next way to do it is to put it in the feedback loop of this op amp and compensate for it. And the way you do that is to break into here. So instead of that output going directly to the buffer there, it's a pretty standard technique if you want to increase the output impedance of your buffer or your amplifier or whatever, is to simply stick that in the feedback loop there like that. Bingo! You've instantly gotten rid of that resistor, and the op-amp compensates for it. Remember, due to op-amp action, this voltage here will be equal to this voltage here. It'll do whatever it needs on the output to make that voltage the same. So you've effectively eliminated the output voltage drop across that resistor, but you still have the advantage that it's protecting the output. So when you short this, you're not going to short directly the output transistors of this op-amp. Beautiful. But that still leaves this resistor up here. Well, turns out we can actually extend that. You can put all of this inside that feedback loop up here, so we can connect that directly to the source pin. So effectively, the voltage, once again, due to op-amp action, that if you set 1 volt here, you're going to get 1 volt there and 1 volt on that pin, and it's going to compensate for the drop through these resistors. So these resistors can now be almost any value you like, within certain limits, of course, and it doesn't matter. The op-amp is going to take care of it for you. Magic. So that's what we're going to do. And because this voltage set here is going to come from a reference voltage. You may want to use a 2.5 volt reference voltage or something like that to match your op-amps of your microcontroller or something like that. So you may not be using, like I say, a 10 volt reference. So you're probably going to need, can't get rid of that. There we go. Probably going to need some gain in there as well. No problems at all. It works exactly the same, not just in the buffer configuration, but also in the gain configuration too. You put all your stuff you want to get rid of in your feedback loop. Beautiful. Whew. So there you have it. After all that design effort, I'm pretty darn happy with this design. I think it's going to be the one I probably build up. Once again, you can add in a second device up here, parallel them like that we've mentioned, stuff like that to increase your output current, and I might do that. And another thing you might want to do is replace this crusty differential amp here with a proper instrumentation amplifier, like I mentioned before, like an AD620, or that's pretty expensive, the lower cost AD623, or one of the high side current monitor amplifier chips you can get specifically for high side current sensing like this, because it's going to be okay at 1 ohm. Like that, you know, just using a fairly jelly bean sort of low-end precision op-amp that has, you know, 500, 800 microvolts or something like that. You can get down to milliamp accuracy on this type of thing. But if you drop that, if you want to reduce your voltage drop across there and use 0.1 ohms or something like that, your general purpose op-amps, even your precision ones, aren't going to cut the mustard too much, and you may as well go to a proper instrumentation amp or something like that. Now, you can do a low side current sensing as well, but as I mentioned before, you're going to get voltage drop across there. If we include the resistor on the ground return path, the current shunt resistor on that ground return path from the output, you're going to get the voltage drop there. There are ways around that, but it's dicky. I don't like it. Stick with the high side current monitor and we're sweet. So, I like that. Let's build it up. Said that last time, but this time, I think I really mean it.